Okay, Assalamualaikum warahmatullahi wabarakatuh. So, all right. So on Monday, we did look into the Fourier series, how you're going to obtain the harmonic spectrum, the Fourier series equation, whereby you can identify the C1, C3, C5, all the Cn, isn't it? For the square waveform, right? So in simulation, we just use the FFT button, the fast Fourier transform, and the PSIM will give you the harmonic spectrum, which tells you what are those sinusoidal waveform behind the square waveform that we had, right? For the full wave rectifier with IDC. And then on Monday we use the fast Fourier analysis to look into how to we can theoretically calculate to get the Cn and so on and so forth, right? So we have done that in the on Monday's class, and we have finished the uncontrolled rectifier. So today we're going to continue with a single phase control rectifier. Right. So as the name implies, single phase is because the input is AC, single phase, and rectifier because it convert from AC to DC. And now we have a control rectifier, whereby for the control rectifier, you know that the output voltage can be controlled. The output voltage can be controlled. So you can regulate, you can modify the output voltage. In order to do that, we replace the diode for the uncontrolled version, isn't it? We have an uncontrolled version, which is the diode that we utilize. But now for the control, we're going to replace that with the thyristors or any other controllable switches. But for the simplest circuit, which is a half wave rectifier, and the rest we're going to analyze the circuit with the thyristor. We're going to use the thyristor in the device. Okay, so we start with a single phase half wave control rectifier, whereby we have this similar circuit, supply voltage and the load, and we have this thyristor. So this is actually the circuit taken from PSIM simulation. Okay, and this is known as an alpha controller. Alpha is the firing angle. Firing angle, which means that you delay the turn on of the thyristor, you trigger the thyristor at certain degree, and that degree is known as alpha or firing angle. You fire the thyristors. Okay, right. So to explain the circuit, we always start with the positive half cycle and we have the negative cycle. So for a positive half cycle, there is no current whatever flowing in at the beginning, right? At the beginning, so there's no current, there's no voltage, anything. And when we have a positive half cycle, the diode is already reverse bias, is in a in forward bias. Yeah, and because this is purely resistive load, the current try to flow, but we yet to trigger the thyristor. So it's still waiting for the thyristor to turn on. So the output voltage is 0 at this time until you trigger thyristor 1 at alpha. Right. So once you have triggered the thyristor, the output voltage now appear as a short circuit. When it turn on, VDC equals to Vy, and therefore it copies the supply voltage until it goes to negative half cycle. The current try to reverse, and then this is a reverse bias, and therefore output will, the thyristor will be off. VDC equals to 0 again until the cycle repeats. Okay, so in this PSIM circuit, we see that the angles here, there are two angles, 45, 46. That means you want a short pulse to be produced by this alpha controller. So the short pulse contains 45, 46. That's it. Okay, this is 45, 46. So alpha only, we know that alpha is 45 degree. 46 is nothing to do with the calculation and converting parameters. This is just to describe that this is a short pulse. In practical, we can also have a train of short pulse. Train. We have a many short pulse, so that we have a long pulse for your thyristor. For some certain application, we do need a long pulse. So that long pulse can be created by using a long a train of short pulse. So that makes it as a long pulse. Okay, right. So let's go further. Once we have this output voltage, then we need to look at the average. So the average is just integrate, okay, to get the output voltage. The average of the output voltage was what? We have this equation of V out equals to 1 over T, and then you integrate 0 to Pt, and then the equation dt, is it? So now we have the lower integral become alpha, and the upper limit, not integral, limit. So the upper limit, we have this as a pi, is it? So that point pi, and this is replaced by 2 pi. So when you do that, you get the output voltage equation, which is equals to VDC V peak 1 over 2 pi 1 plus cos alpha. So in this equation, we see that there is a control parameter variable in your equation, and therefore you can vary the VCDC. So if alpha equals to pi, this term goes to -1, isn't it? Cos pi will be -1, so you have 1 minus 1, and therefore pi equals to VDC will be equals to 0. So if you look at the waveform again, so we have this output voltage. As you increase the value of alpha, right? So the voltage, as you increase the value of alpha, so you're going to see that the output voltage becomes smaller here, right? And then smaller again until pi, isn't it? So if alpha equals to pi, then this is completely 0 all the time. So that's why VDC equals to 0 when alpha equals to pi, right? So that is the output voltage. And then next we look into the resistive and inductive load. In this case, you just extend what you had learned during the uncontrolled rectifier. So if you have an uncontrolled rectifier, during positive half cycle, the diode will be turned on, isn't it? It will be turned on, and at the negative half cycle, because of that inductor in the circuit, the current still continue to flow in that direction. So this is clearly shown with this waveform, the current waveform. We can see that the current is still positive. That means there is still current flow in that. This current will force the diode to stay, the thyristor to stays on, and therefore the output voltage still copy the Vs. So that's why it goes to negative until the current goes to 0 at the extinction angle. This is known as a extinction angle, where the current equals to 0. And for the thyristor, so here we have this alpha, is it? So at beginning, the output voltage is 0 because the thyristor is not turned on yet. It wait until you trigger or you fire the thyristor at alpha angle, and then the current rise. Then we have beta here. Okay, so similar happens here. You just integrate now from alpha to beta. The lower limit is alpha, the upper limit of beta, then you can get the output voltage equation. And for beta, how to find beta? We need to identify the current equation. Once we know the current equation, and we know that at I beta, the current equation equals to 0, and the current goes to 0. So we need to have this current equation. Then we set to 0, and we use the calculator. Is it? Last week we did one to find the beta for the uncontrolled rectifier. So that similar happens here. So if you look further, this is the output voltage. Okay, output voltage. Again, you have the control parameter, control variable here, alpha, to change the output voltage. And this is the current equation. So I did not show the derivation of this current equation. You can try it at home. Use the superposition theorem, right? When we consider the forced response and natural response, and now we have this alpha in this equation, right? So you can try to derive, right, and get this current equation. And this is the current equation which will give you the value of beta, because we know at alpha beta the current equation equals to 0. Okay, so this current equation will be used again. Remember, this current equation will be used again when you analyze the full wave rectifier with R plus L circuit later on, right? So this current will be used again to determine whether the current is continuous or discontinuous, right? Okay, so next let's look at the resistive and inductive load with freewheeling diode. So we notice that when we look at the output voltage for the resistive and inductive load conditions, there is a negative area. So this negative area will actually reduce the available output voltage, right? So of course we want to have the high, as much as output voltage available for the output, isn't it? So this is because of that R plus L condition. There is a negative area, so that negative area actually reduce the output voltage equation value. So the average become lower. So if there is a method to remove that, that is good enough. Therefore we have more available output voltage, more available load average voltage at the output. So how to do that? We just simply place a diode in parallel to your load. Okay, so you have just simply put the diode in parallel to the load. So let's look at what happens in that time. So we have a freewheeling diode there, and we know that current flows in this direction. Okay, so positive half cycle, we see that this is forward bias, and then it wait until alpha to be turned on, and during that time, during positive half cycle, this diode is also for reverse bias. If we have a reverse bias of the output the diode, so it appears as open circuit, and then we see that the current, so in this case the current is continuous, right? It's a continuous output current, so there is always a current flowing in clockwise there. So during positive half cycle, similar what happens to the circuit just now. At this alpha, the output voltage copy the supply voltage until negative half cycles. Now, because this is reverse bias now, and this is forward bias because it's reverse, so it become plus minus, and we have a current flow. Instead of it flowing to that path, the current will flow through the diode. Okay, so turn on the diode, so this appear as a short circuit, and therefore VDC will be equals to 0. So that's why if you look at this part, the output voltage become 0. So there is no more beta here, there's no more negative area here. So the output voltage become 0 until the next cycle. So there is no negative area and negative voltage, so therefore the output voltage is more output voltage, average output voltage is available, even though we have R plus L at the output. Okay, so what else can we observe? We can see that the input current now, the IAC, the input current, which is the current through the thyristor here, will jump. It jump from highest peak here, almost a peak value, to 0 instantaneously. So it's just like a human being. If you jump from a second floor, third floor, of course you will feel more stress, isn't it? I mean, you can badly hurt if you jump from higher level, isn't it? So in this case, because of that operations, we see that the thyristor have more stress it become more stressful in this case, because the current jump from peak value to zero instantaneously. So that is the observation that we can do. And there's a note here, advantage. Because of that, we increase the average voltage, and the disadvantage is that the supply current becomes sharp edges. Okay, so this is the output voltage equation, similar to the previous equation when we have a R case, purely resistive load case. Next, we look into the freewheeling diode, and we place the the back EMF. We have the DC motor at the output to replace the DC motor, and then we have the freewheeling diode in parallel to your load, the DC motor here. So very similar. At the beginning, there's no current flow, everything. So VDC, this is open circuit, this is open circuit. We talk about 0 seconds at this point, 0 second, and there's no current flow, so therefore V across R and L also 0. Therefore VDC will be equals to back EMF voltage, which is in this case is 100 volt, so it will have this 100 volt at the output voltage. So that's why we have that 100 voltage. It doesn't start at 0, but start with 100 volt. And when you turn on alpha, then VDC copies the supply voltage again, and that's why it follow this supply voltage until negative half cycle. During negative half cycles now, instead of the current flow, then similar happens, the current flow into your freewheeling diode, turning on the diode, and therefore the VDC equals to 0. 0 until this current goes to 0. Because of that back EMF, so back EMF, the polarity of back EMF is plus minus, and the current in the inductor is in that direction, so it is opposite direction of the current here, isn't it? So it opposes the current, and that's why it forced the current here to go to 0. So that current goes to 0 again at beta. When the current equals to 0, VDC will be equals to 100 volt again, because this is off, right? So therefore VDC equals to 100 volt again. So that's why after that we have beta equals to 100 volt until the next cycle. So here we need to have to integrate again. V out is integration 1 over T of the integrate, so this area under the curve. So we have one area here, two area here, and we need also to integrate that area as well, to get that function, to get that area. Okay, so when you do that, you have this. I don't want to go through this. You try to have a look. We have this VDC equals to E minus 2 alpha plus the rest. Okay, so back EMF forces the DC current to be 0. So that back EMF oppose the current, DC current, and that's why it goes to 0. Okay, so now we look into the single phase full wave control rectifier. So in this case, we start with a resistive load. So again, this is a similar explanation, just you all modify the starting of the diode or the resistor. So previously for full wave rectifier, T1, T2 will be turned on during positive half cycle, T1 and T2 will be turned on during positive half cycle, and then T3, T4 will be turned on at negative half cycles, isn't it? Okay, so this is the uncontrolled rectifier. So with this control rectifier, again, during positive half cycle, T1 and T2 is forward bias. Okay, T1, T2 forward bias, but it waits until you fire those two thyristors at alpha angle, the firing angles, and after that, then the output voltage copy the supply voltage, and then when it's a negative half cycle, T3 and T4 is forward bias, and then it waits the T3, T4 to turn on, and notice that this is alpha for T1 and T2. for T1 and T2, the diagonal thyristor. Okay, the diagonal thyristor will receive the same same angle, alpha 45 degree, and T2 also receive 45 degree. And for the other diagonal thyristor, the thyristor 3 will receive alpha plus 180 degree or pi. Okay, it will receive alpha plus 180 degrees. So that's why you have 225 degree for the other diagonal thyristor. So here we can see that this is 45 degree and this is 225 degree. Okay, right. So next is that look at the average voltage. I'm not going to do with you, so just look at the derivation. Again, please fill in the gaps, right? This is your responsible to fill in the gap, not only just memorize that, but try to do the derivation to get that equation, final equation here. Right, so next, resistive and inductive load. Now we have a more complicated circuit. I mean, more conditions to consider, right? And for resistive and inductive load, R plus L, there are two conditions to consider. One is discontinuous output current, which means the output current here become discontinuous. So you can refer to this current, right? So this is the IDC, the output current is the red current here. And if you look at the output current, it becomes discontinuous, which means it drops to zero. Drops to zero and then stays at zero and then increase again, drop to zero, increase again. So if you look at this input or the output current here, it resembles the half-wave rectifier waveform. Is it? The half-wave rectifier, so whereby we have alpha here and then we have beta there. Is it? Okay. Alpha is there and then we have beta there. So here we can see that this is your beta minus pi, the angle. This is alpha, this is beta, this is alpha plus pi. Right? So at the beginning, we can start with, let's say there is no current at all at the output. There's no current at all because at the beginning, of course, you start with zero, everything reset to zero, current is zero, VDC current, everything should be zero. So we start with a flat. I mean, let's say this is a flat. I mean, start from zero, eh? So ignore that at the beginning of the simulation, for example. So we start at 0 voltage here. Output voltage equals to 0. And then we trigger thyristor 1 and thyristor 2 at alpha, isn't it? Okay, and then the output voltage copy the same supply voltage until the negative half cycles, and there is a current still flowing in the output, and therefore it forces T1, T2 to turn on until beta, which is the current goes to 0 at that point, isn't it? It goes to 0 at this point, and therefore after that the output voltage becomes 0 again, and then at alpha plus pi you trigger thyristor 3 and thyristor 4, and therefore your current the output voltage follow the shape of your supply voltage until the next cycle it follows. So finally, if you look at the steady state output voltage, this is what you get. The output, the waveform. Okay, so this is beta minus pi, alpha is beta. So this is the case of discontinuous output current, and that can be determined. You can find the whether the you can determine, or you can calculate, or you can determine what is whether it's discontinuous continuous output current by finding the value of beta, and then beta must be less than pi plus alpha. Look at that. This is your beta. This is pi, isn't it? This is beta pi. This is beta, and this is your alpha plus pi. Okay, so if you calculate and you find that the beta is less than pi plus alpha, so definitely this is discontinuous operation. So how to get this beta is by looking at this current equation, isn't it? To get that beta, we need to find the current equation for this circuit. And if you look at the current equation waveform, this is similar to the half wave rectifier. Okay, the half wave rectifier that we had before when we consider the R plus L circuit. Okay, so the equation is, you can reverse back, and that is the equation, right? We have the condition of R plus L and this current, the similar current here. So if you can find beta here and then you compare with alpha plus pi, so discontinuous condition, beta must be lower than alpha plus pi. If a continuous operation, beta must be greater than alpha plus pi, right? So in this case, so this is the equation that we need to use. Okay, so let's go to resistive inductive load. Go back to that node. Right. First we look into the output voltage equation. So to find output voltage equation, you just need to integrate this portion and then that portion. There's two integral. One is that integral and the other one is integral, and for this it is from 0 to beta minus pi, and it is negative of that equation, isn't it? Negative of that equation. So this equation is V peak sine theta. So in this case you have minus V peak sine theta. Minus V peak cos theta. So that's why you have this equation, right? And t now become pi. Instead of 2 pi, it is pi. It repeat by pi. So you have that equation, and finally you have this equation. Okay? So that is the average value of the discontinuous operation. This is only for discontinuous operation. For continuous operation, when you look at this again, you see that this is the case where beta greater than pi plus. Okay, so if you look at the current is continuous. It continuous operation. It always continue to operate. So in this case, let's start with 0. Okay, do not consider this. Start at 0 voltage here. No current flow, everything. So at alpha, then we have this VDC equals to V out, and then during negative half cycles, the current still flowing, forcing tester 1 and 2 to turn on, to stays on. Okay? So you have this still current flowing, still current flowing, still current because it's continuous. Okay, continuous current. Still there are current flowing, forcing tester 1, tester 2, but T1, T2 is reverse bias. Okay? It's already reverse bias, but during that point, we trigger tester 3 and tester 4. In this case, tester 3 and tester 4 will be conducting the current, and T1 and T2 stop to turn on. So it will be turned off after T3 and T4 is turned on. So T1, T2 off, T3 and T4 will start to turn on, and therefore the output voltage become this, right? Become that. Okay, so there is a difference between discontinuous output current and continuous output current in terms of the output voltage. Okay? So you can integrate again to get the average. You integrate from 0 to alpha, and this again minus V peak sine theta, and that will be from alpha to alpha plus pi. From alpha to pi. Right? You just integrate up to pi, and that gives you equation this equation 2v peak over cos alpha. Right, so let's go back to how to find the beta. Okay? How to find the beta, because that beta will determine you current. So let's look at the current. Let's look at one example. Let's say we have this situation. This is, let's say we start with 10 millihenry. Okay, we start with 10 millihenry. R plus L. R is 10. We have 240 volt square root. This is sorry, with uncontrolled. No. Okay, that case. Wait. All right, in that case. Single phase full wave. And this is 10 millihenry. And this is 240 volt multiplied by square root 2. Okay, so this is your condition. Okay, so let's say we have this circuit. We want to find out whether this circuit falls under continuous current operation or discontinuous current operation. Okay, so in order to do that, we have this equation. We have this equation. So we need to find the beta using that equation. So in this case, we know that alpha can be found. And we have this R minus R over omega L. One thing is, I need to share with you, there's another variable which is known as a time constant. Okay, when you analyze R plus L circuit, you need to always to consider this time constant. Okay? So this time constant is the, what we call it, for the rule of thumbs. When the circuit gets into 5 times of the time constant, the circuit normally has come into the steady state condition. It reached the steady state condition. Okay, 5 times tau. So what is a tau? Tau equals to L over R. Right, so whatever the L you divide by R, that gives you the tau equals to L over R here. Okay, so here we can modify that. Therefore, you have minus theta minus alpha divided by omega tau. Okay, you can also have that equation. Right, so in this case, you can try to use your calculator. So just simply calculate what is, so we need to find what I beta, and then at beta I beta equals 0. So if you set this equals to 0, then you can see that this term goes to 0. So what left is only sine beta minus v plus sine v minus alpha e minus r over omega L, and then we have theta minus alpha. Okay, so again, please make sure that you evaluate or you calculate, and your mode must be in radian. So everything should be turned into radian. Right? You must convert everything into radian instead of degree. Remember that. Okay, when you want to deal with the control rectifier, everything's a rectifier equation, make sure that is converted into radian. Yeah, the mode is in radian. So you can find that easily. You can use the calculator, calculate one by one, right? And make sure that the initial value of beta is always pi, which is 3.4 something, 3.14, isn't it? Because we know, we look at the current equation, it is always exceed the pi value, isn't it? It's always greater than 180 degree. So when you do the calculation, use the calculator, make sure that the initial value of beta is 3.14 or pi. Okay, so again, I'm going to share with you. You can also use the software, and I will recommend you to use the MathCAD. Right, so this is the MathCAD, MATHCAD. So make sure that you use that, right, to help to assist you in studying this powertronic, and you can use that anywhere actually, and not only for the powertronic. You can solve and many equation by using this MathCAD. Okay, so you need to define first. You need to define everything, and then this is the equation, right? Just now we have the current, isn't it? V peak over Z sine plus V peak equals to 0. Okay, so in this MathCAD, you need first to define the initial value. Okay, this is initial condition, beta equals to 180 degree. I multiply the degree because beta should be the MathCAD always consider the when you do the sine beta here, it always calculate in terms of radian. So you need to convert that 180 degree into the radian. In order to do that, I just multiply by degree, 180 degrees. So this is a what you call it, pre-program variable to convert from degree to radian. So you just simply 180 multiply by degree. Just write degree, so it will convert beta into. So if uh, I mean this beta, this initial value is 180 degree, and then you write given. You must write this given words, and then you write the equation, and finally you just simply use find button. Okay, you just simply find button, right, and it will give you the question. This is the case of 100 millihenry. So 10 millihenry. Just now we have 10 millihenry. So L equals to 0.01. Okay, so in this case, when I do that and solve, I get 197.35. Make sure that you use calculator. Okay, and then this software, if you have time, play around, because this will save you time and that will verify your calculation, your calculator, the result from your calculator. So you'll become more confident because you have calculator, and then you have the software to verify your answers. Okay, so I did that and I have the answer of 197. So if you check again, we have beta now equals to 197, and we need to check with alpha plus pi, isn't it? So alpha is 45 degree plus 180 degrees, so this is 225 degree. So now the condition is beta is less than 225 degree, or alpha plus pi, isn't it? Right, it's less than degree. So if I simulate, I will get the current equation is discontinuous. Okay, so I'm going to show you. So if I go back to that, if I run this circuit, okay, look at this. This is the input current, IAC. Look at that. If I look at the if I put in the IDC, where's IDC? So there's no output current. I'm going to put that output current here. Okay, so this is the output current. Run again. Okay, so now I'm going to place if I can. All right, let's look at it. So now we have the output current become discontinuous, and that has been verified by the simulation. So this is beta and this is alpha plus pi z. So it is discontinuous. So that happens when my circuit, when the circuit is with the 10 millihenry. What happens if we change that to, let's say that the alpha now becomes 100 millihenry? Okay, 100 millihenry. So let's look at the math cat. Rather than I am going to put my use my calculator, I just simply place or replace this to 0.1, and I already get the answer of 429.23 degree, and therefore exactly beta is higher than the alpha plus pi z. So in this case, I will expect that when you do my simulation, the output current become continuous. So I'm going to do that, run simulation. Look at the output current now. It is continuous, and therefore the output voltage is become this. Instead of just now we have it goes off there, and then it goes there. Isn't it? So the operation now falls under continuous output current. Okay, so please try to use the PSIM, try to use the MathCAD, and practice to use the calculator, your shift solve everything, to get the value of current, the beta. So now we proceed to look into the square waveform just now. All right, so just now we have a, let's say that we replace the output current, the output side here, with a constant current. We want to analyze a constant, a highly inductive load operation. This inductor is very high, so we want to consider that. So we replace this with a constant current at the output. Okay, we want to look at this current. So if I can simulate that. Okay, I'm going to switch to IDC. So this is the case. So we have 10 amp. We still have the same 45 degree and the rest. I'm going to simulate that, run the simulation. So this is the output input current. Okay, and this is also an input current. So if I want to make it larger, I'm going to multiply that IAC to increase the value. So I'm going to multiply by 10 by 5. So to make it bigger, so it will be clearer in the so this is similar waveform current, but then this is increased by a factor of 5. I just want to make it appear in this waveform. So this is my supply voltage and this is my current. Because of that alpha, it shifted to the angle of alpha. Before this, when we analyze the full wave rectifier with a highly inductive load, uncontrolled version, it start at 0, isn't it? So your current start from there, the square waveform. Okay, the square waveform start from there, then dies on pi, goes down to negative VDC, again 2 pi, that is it. So this is a case of uncontrolled rectifier. The square waveform start at 0, but because this is a control rectifier, the square waveform start at alpha. Okay, and if I use the fast Fourier transform, click that, and if I look at the square waveform again, it is very similar to what we had before, which means you have the same C1, C3, C5 and the rest. So there is no difference between control and uncontrolled rectifier, between square waveform for the that start at 0 or the square waveform that start at alpha. No problem with the magnitude. So you have the same C1, C3, C5, the rest. But the problem is, if you look carefully, okay, if you consider this, okay, the fundamental of this current, okay, remember when you do the harmonic spectrum, it gives you the value of fundamental, the sinusoidal waveform current at fundamental, which is, if you consider fundamental, so it will probably I need to get higher. I need to multiply 10. I want to make it larger value. Alright, so that is my current waveform. So this current waveform actually is made of the fundamental, which is the sinusoidal current, sorry, so let's do it again. Okay, the sinusoidal current. So this is IS1 and the fundamental component, which is at 50 Hz, and the amplitude here is known as IS1 or C1 with the peak value C1, isn't it? Okay, so if you refer to that, there is a there is an angle between the sinusoidal voltage and the sinusoidal of the fundamental current component, and that angle is known as alpha, isn't it? The firing angle. And before this, we have phi n, phi1 equals to 0, isn't it? When the current at 0, when we have a square waveform, 0 voltage here, of course, phi1 equals to 0. But now, phi1 equals to alpha, right? In that case, when you want to find the, clearly shown here, right? So we have alpha there. You have the same THD, total harmonic distortion, still 48.4%. But when you want to calculate this power factor, you will get a different equation or value. Okay, so we know that alpha equals to phi1 is now alpha instead of 0, and therefore the displacement factor cos alpha can be calculated with that if you know the alpha, and then the power factor now become 0.9 multiplied by cos alpha. So the power factor is no longer 0.9. Before this, if you remember, we would have one problem. The power factor is 0.9. THD is 48.4%. So for the case of control rectifier, the power factor is depends on the value of alpha. Okay? It depends on the value of alpha. And next, just simply resistive inductive load with freewheeling diode. Similar explanation. We want to remove the negative area here. Okay, so we place the freewheeling diode. So during negative half cycle, the current flows into that. So the output voltage become short circuit. So that's why we have voltage is 0. Okay, and next with a back EMF. Okay, you can explain this. For back EMF operation, the current is always discontinuous. There is a continuous, because why? This large voltage here will force the current to become 0. Is it? Without that, yes, without the voltage, the current can be continuous. But because of very large voltage, usually we have a very large voltage here, so the current will goes to 0. Okay, so when the current, we can start to explain. If you from we can start from uh, we positive half cycle, And then if you start at 0 seconds here, no voltage, no current flow and anything, and therefore if there is no current flow, V out here will be equals to 180 volt. So at the beginning, if you consider from 0 seconds, I'm talking about 0 second, we start at E until you trigger thyristor 1 and thyristor 2. This is thyristor 1 and thyristor 2. And then during negative half cycle, the current flow into the diode, short circuit, and that's why you have 0 voltage until your current goes to 0. When the current goes to 0, the output voltage again equals to a back EMF, 180 volt, and then the cycles repeat. So this is the current equation, the voltage waveform and the current waveform. So you have beta minus that, and you can find the area in the curve to get the average voltage, and that's it, isn't it? So that is probably we're going to continue with that next week on the effect of having source inductance. Okay, what happens to the circuit if you have this source inductance at the front end? Okay, all right. So have a look, and there's a one assignment. I just want to force you to do a PCM and to look into the Fourier series. Right. So we come back to view, navigation pane, bookmarks. I want to come back to the resistive load. Very simple. Yes, problem number 2 here. Okay, so this is the output voltage, or output voltage and the current. So I want you to do this. Calculate the DC first by using the using the Fourier analysis. Okay, show me the step to get the Fourier series, so that you can calculate what is a DC, what is the first. DC is the average, isn't it? The average value, but you need to analyze the circuit, whether it has a symmetry or not, and then try to perform AN, BN. Okay, you show me that first so that you can verify the answer. 1.08, 1%. So, and finally, I want you to use the PCM. Use the PCM, use the FFT function to get this harmonic spectrum at 108. Then you have second harmonics, third harmonics, and whether you have 0 at third harmonics. Okay, right? So that is the assignment number 1. I'm going to share with you through WhatsApp again the assignment. What you need to do. So maximum 3 in the group. It's a group assignment, or you can decide to do it alone if you want, no problem, but it due in 1 week. It will be due in 1 week, inshallah. Okay, thank you very much, and don't forget to, you need to watch this through Add Puzzle. Make sure that I will update you whether you cannot miss any seconds. You can stop, but you need to start from just before where you stop, right? So that there is no section left. Then you will not get 100% in the Add Puzzle. Okay, thank you very much. See you next week. Assalamualaikum warahmatullahi wabarakatuh.